Hello, ladies and gentlemen. So today, what I want to do is I want to talk about how to graph y equals 3 sine of 2x minus 3 pi plus 5. Today, we're going to use this systematic technique. Okay, and so let me just outline the way we're going to do this. We're going to first find the period that the graph is gonna have, and remember the period is how long on the x direction the function needs to repeat itself, right? The period being the portion of the graph that repeats. We're going to find the starting point, um, and then we're going to graph it, okay? Keeping in mind our landmarks, in this case of the sine, but if we were graphing a cosine, of the cosine, okay? But in this case, since it's a sine, we're going to deal with the landmarks of the sine. Okay, so let's begin. We know that for the sine, the cosine, the secant, and the cosecant, the period is equal to 2 pi b, where b is the coefficient of the x or the theta inside of the sine. So in other words, in the general case, it would be sine of bx plus c, and so the period would be sine of 2 pi over b. Here, b is 2, so 2 pi over 2, which gives us just pi. So in other words, this graph will repeat itself every pi units in the x direction. We now need to find the increment, okay? The increment will always be the period over 4. Now, this formula for the increment holds for all trigonometric functions: sine, cosine, tangent, secant, cosecant, cotangent. But the period, this particular formula, only works for the sine, the cosine, the secant, and the cosecant. Okay, anyway, now for the starting point. To find our start point, we're going to set this expression inside of the sine equal to 0 and find out what x has to be. So 2x minus 3 pi equals 0. I want to get the x by itself. I want to isolate the x. Since we have 2x minus 3 pi, I'm going to plus 3 pi to both sides. Because remember, whatever we do to one side of the equation, we can do to the other. Or in fact, we must do to the other, right? So we get 2x equals to 3 pi. 2 times x equals 3 pi. To undo the multiplication by 2, we divide both sides by 2. So divided by 2, divided by 2, we see that x is equal to 3 pi over 2. Okay? So we're going to consider that our start point. Now let me just remind you what I mean when I say that this is the start point. And now we're going to relate it to the major landmark points of the sine. Okay? Okay. Okay. So we remember that the parent sine function goes like this. Right? That's one period of the sine of the parent function. And this is at x equals 0. This is at pi over 2. This is at pi. This is at 3 pi over 2 here. And this is at 2 pi. Right? And of course, the values are respectively negative 1 here, the y value. The value here is 1. And then this one, this one, and this one are 0. Right? That's our parent function. So what this start point does, because of the way we chose it, it makes the inside of the sine 0. So when sine, the function, sees 0 inside of it, irrespective of what is actually inside of it, like as an expression, but since it sees 0 here, the sine will output 0. So in other words, at this point, sine will see 0. And so when I say the start point here, what I mean is that this pattern of the graph will start for this graph at x equals 3 pi over 2. Okay? So in this case, since this is positive, then it'll start going up and then down and then going up again. But instead of being these numbers, it'll start at 3 pi over 2 And then we're going to use the increment, which here is period divided by 4, which was pi over 4. So we're going to do 3 pi over 2 plus pi over 4 to get the corresponding point for this one, plus pi over 4, the increment, to get the corresponding x value here on this graph, and so on and so forth. So let's do this on the real graph paper here. Okay? Okay. So since it's in terms of pi over 4, the increment, I'm going to make this one in terms of pi over 4 just to make our lives easier. How would I make the denominator 4 without changing the value? Multiply the bottom and the top by the same number. In this case, 2. So 6 pi over 4. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now let's look at these y values. We know that sine takes on the values from -1 to 1. So if sine takes on the value -1, -1 times 3 will be -3, plus 5 will be +2, okay? When sine is +1, 1 times 3 is 3, 3 plus 5 is 8. 2, 3, 6, 8. And so here, what I want you to notice here is I have basically what I've basically done here is I have found the upper and lower limits of the graph, namely the values that are going to correspond to the top of the graph and to the bottom of the graph respectively. Okay? So now, again, this bottom is in terms of pi over 4. So 1, 2, 3, 4, 5, 6. So this point is 6 pi over 4. And in fact, in this case, I don't have to put it so much down, but you know, okay. 7 pi over 4. Notice I added 1 pi over 4, which is one of the increments. I add pi over 4 again, so 8 pi over 4. I add pi over 4 again, 9 pi over 4. And I add it one more time to get 10 pi over 4. Now remember, we add the increment once, twice, 3 times, 4 times, because if we start 0 on the parent graph, we go plus 1 increment, plus 2 increment, plus 3 increment for this point, and then plus 4 increment. So we always add 4 increments to get the complete period. So now watch this. Since this was the starting point, we know that the sine will see a 0 in here. So the sine value at 0 will be 0. Times 3 is still 0, plus 5 is 5. So I can see that at this point, the value that the function will take will be this value here, okay, which is 5. And because the graph is going up to the maximum at the next point, at the next increment, we can already know that it'll be here at 8. Then the graph comes down again, like this. So it'll be back at 5 at the next increment point, here. Then we go one more here, and we're going to be at the bottom. So we're going to be at 2 at the next increment point, here. And then finally, at the next increment point, we'll be back at our starting point, which is here. Okay? That's one period of the graph. This is how that graph will look. So I want to recap really quickly how I got this period, and then I'll show you how we can stretch it out to fill out more points and stuff like that. Okay, like if we want 2 periods of the graph. So basically what I did was I first found the period. I then found the increment. The increment corresponds to the spacing between the landmarks of the parent graph as far as on the graph we're looking for, right? And the start point is where the pattern begins. So here, the sine of the parent starts at 0 and it goes up and then down and then back up again, okay? So if I use the starting point that I find by setting the inside of the sine to 0, then I know that the pattern will begin from there, going up, then down, then coming back up again, using my increment to hit the major landmarks. Now, if this had been a -3 instead, the only difference we would have done is that instead of going up, down, up, is we would have gone down, up, down, right? Because a negative on the outside would have flipped the parent function, right? So instead of going like this, it would go like this, okay? Or I mean, the parent function never flips, but I know you know what I'm saying, right? The y value, instead of being positive, would have been negative, and the y value, instead of being negative, would have been positive, right? Okay. Now, there's something I want to talk about here. We're just going to briefly, oh no, okay. We'll continue with this discussion, and then I want to make a little detour. Okay, so as you saw here, I drew this x-axis so that each of these sticks corresponds to pi over 4. That means that if we go backwards, we will keep hitting the landmark points. And that means that if I start here, then if I go 1 to the left, as for increments, I'll be going down to here, just 2 right there. And then if I go 1 to the left more, increment-wise, then here, I'll be back at 5. Then if I go 1 increment back more, I'll be up at the top again. Let me see, is that right? Oh my god, I went too far. Okay, like this. And then if I go 1 more increment back, I'll be at the start. So let me see here. 1, 2, 3, 4. Like right there. I was just trying to see it vertically so it would line up because I'm looking at it from close. And so that's a second, wait, what? Oops. Yeah, like this. Like that, right? If you notice, since I started from here and I went backward, I just duplicated the path, right? And I can keep going, right? If I go 1 more like this, then I'll be back at 2 again. And then if I go 1 back this way, I'll be back at 5 again. And so I'll be like this, okay? And I can keep going that way if I want to, just following the pattern, right? So in this graph, we see 1 full period here, and then another full period here. So this graph has more than 2 periods. Got about 2.5 periods. Okay. Now I want to make an important point, and I think some of you may have caught this, but if you didn't, that's okay. Not that any of you to catch this, but it can be helpful. Okay. So what I wanted you guys to notice about this, or not what I wanted you guys to notice, but what I noticed in this example and that I wanted to bring to your attention was that this starting point was at 3 pi over 2, right? Now, the period is pi. In our brains, we can think pi equals the same thing as 2 pi over 2, right? Right? And so therefore, since the period is the portion of the graph that repeats itself like this, and if my aim is just to graph the function, right? Instead of plotting it starting here, what if I subtract 1 period and start plotting it from there instead, right? So in other words, if my starting point is, for whatever reason, let's say inconvenient to me, or I just choose that I don't want to use that starting point, I can add or subtract the period until I find the portion of the graph that I want to curve. That I want to draw. Okay? So if I subtract 2 pi over 2 from here, right, that would be 3 minus 2 is 1, 3 pi over 2. I just subtracted 2 pi over 2 from here to get an alternate starting point. Okay? And then I can just translate this into a denominator 4 by multiplying the top and bottom by 2. So 2 pi over 4. Okay? So let's look at that here. So there's 6, there's 5, 4, 3, 2. Now, I want to be clear here. What I want you guys to notice is this. It is in fact the case that when we found our original start point, we set this inside equal to 0, and we then solved it for x to find the start point. That is still legitimate. But once we get one starting point, which means the point on the graph of this curve in the x-axis where the pattern starts, right? If we subtract 1 period from it, or 2 periods from it, or 3 periods from it, or 1,000,000 periods from it, we will also find an x value where the graph will start the behavior that the parent exhibits. Okay? With the slight caveat that I mentioned earlier, that if the 3, for example, was negative instead of positive, that we would see the pattern in reverse. But of course, here it's positive, so it just has the same pattern. So from what we said is that at this point, we're going to start it. 0, 0 times 3 is 0, plus 5 is 5. So that'll be here. I apologize that I have to get in the way of it, but because I'm so close, if I look at it from the side, my graph might end up lopsided and then it'll be more ugly than it is, right? At the second point, it'll be at the top. So it'll be at 8. So here, at the third point, I'll be back at the midline, let's say. At the fourth, I'll be at the bottom. And at the fifth, I'll be back at the repetitive part, or at the start of the repetition. And you can see that that's exactly where we would expect it to be, because that's where the next period starts. And in fact, as you can see, that's exactly the 6 pi over 4, the original starting point. In other words, where the pattern begins. Right. So in other words, I could have started the graph from there, and then I would have continued it just as before, because the pattern repeats. Right, I'm just going to draw this real quick here. Okay. So if we want to, we could start this, knowing the period, we can take the start point we created and just add or subtract the period to find a portion of the graph, or an alternate starting point to draw the graph. Okay. Okay. I hope you all have enjoyed this example, and I look forward to seeing you guys again soon. Thank you.